We are excited to have our speaker, Finale Doshi-Velez, here today. She is an assistant professor in computer science at the Harvard Paulson School of Engineering and Applied Sciences. Her research focuses on the intersection of machine learning and healthcare, and today she'll be speaking to us about interpretability towards more rigorous evaluation.
Awesome. Thank you. Hi, everyone. It's exciting to be here. I like to keep talks fairly informal, so if you have questions along the way, please shout out, and we'll also have questions toward the end. One thing I want to point out, I'm going to share a little bit of the work that we're doing currently in our group, but more importantly, the thing that I want to chat about is how we can make interpretability more rigorous. So it's a bit, this talk is going to have more of a philosophical or forward-looking component rather than a ton of results that are already completed components. And that's why I encourage everyone, if you have ideas, to really engage in the discussion, because that's what I'm really interested in having. So just to get started, you wouldn't be here if you weren't interested in interpretability. It's definitely in vogue. Tons of publications coming out, especially lately. If you just look at Google Scholar hits, obviously the rate of publications in general has been increasing, but you see there's huge numbers of publications in the last several years under this guise of interpretability in machine learning. And part of that interest comes from the fact that machine learning systems are being deployed in more and more settings and as part of more and more systems. And now we are curious about, well, are these systems behaving in ways that we expect? Are they latching on to signals that we didn't expect? How can we ensure that our systems are doing what we want them to do? And how can we debug them when they're not doing things that we want them to do? Hence this growing interest in interpretability. But the big question is, what exactly is interpretability? And that's the thing that I want to chat about today. And also, how should we go about quantifying and measuring it, both from a human perspective, and also, is there a way to distill it down so that we can optimize for interpretability, maybe without all of those expensive human subject evaluations? So those are the sorts of things that we're going to be chatting about. So first, let's start out with this question of what is interpretability. So if you look at a dictionary definition of the word interpret, which is the root word for interpretability, it's to give or provide meaning, to explain. And I think that explanation is actually a much more human, tangible word than interpretability. Right? It's easier to think about what is a good explanation. Have I explained something to you? Because you can think about whether do you understand it or not. Right, so that's the term that I'm really going to be thinking of, and I'm encouraging you all to think about when you think of interpretability is the question, what's the quality of this explanation? And before I go forward, I also want to distinguish the word interpretability, or the process of providing explanation, from a lot of other words that we also see as auxiliary criteria for our machine learning systems. So there was a time when we were just interested in prediction. So we just need a system to predict. And now we're often interested in other criteria as well. So there's been a lot of recent interest in transparent systems, in accountable systems, trustable systems, fair systems, systems that produce actionable outputs, systems that are robust or reliable, systems that are safe. And some of these areas, I forgot privacy. Privacy is another one. So there's a lot of these sorts of terms that are being bandied about. And some of them, like privacy, they have very clear, there's some at least attempt at making a rigorous definition. For example, differential privacy has a very clear mathematical formalism. You can verify whether a system is differentially private or not. And we don't have that in interpretability. And one of my goals is to get us closer to thinking about what those sorts of definitions should be. The reason I distinguish the process of explanation from these other criteria is that oftentimes we fall back on interpretability or the need for explanation because some of these other criteria are also not particularly well quantified. So we want a system to be safe, for example. What if we can't list out all the situations in which an unsafe scenario might happen? We might fall back on, well, if the system can at least explain what it's doing, then we're in a good position to identify whether something might be safe or unsafe with a bit of human checking, right? So interpretability is this thing that you do mostly probably in the service of something else, right? So let's actually think about what reasons you might need for interpretability. So one area that I work in quite a bit is in healthcare. So we are interested in deriving disease subtypes. We are also interested in identifying what treatments work best for what patients. And in this case, there's a clear scientific question of like, what is disease? How does it progress? How do drugs interact with the disease process? And interpretability is really important because we are looking at large amounts of data, but at the end of the day, we actually want to have some new insights about the mechanism of human physiology and pathophysiology. Another reason why you might want interpretability is to be able to debug your system. You have no idea why the system's not working, but if the system can give you an explanation of how it's coming to its decisions, maybe you can identify why that decision is wonky and find the issue in the system. I already mentioned the issue of safety. Again, maybe you can't identify all the scenarios under which a system might be unsafe, but at least if it tells you at any point what you might want to do or why it's making its decision, you can decide what you want to do with that decision. Another big area category that I put here is mismatched objectives. So going back to the clinical scenario, sometimes we have a thing that we're interested in terms of output. So for example, if you have a patient who is depressed and you want to manage their depression, then that's the criterion maybe that you're trying to optimize. But it might also be the case that that patient is averse to weight gain. And so there might be this auxiliary or secondary objective that you were not aware of. Or maybe there's a particular drug that requires being taken 3 times a day versus a drug that's being taken once a day. And depending on the patient, the probability of adherence may be different for those 2 regimens. And if you had those written out, then maybe you could write them all down and you could put them into an objective function. Or just solve the multi-objective problem. We know how to find Pareto fronts when we have multiple objectives, right? Again, there's no interpretability required there. But if we don't actually have the full objective at the time, and maybe the human is not even aware of exactly what they want, then you run into this case of mismatched objectives, where you need a little bit of explanation that might suggest why this was chosen, but maybe you can also decide that you want to do something else and change the final decision. And the final one that I'm going to point out is in a legal setting. So EU regulation is going to require all systems, algorithmic systems, to provide explanation starting in 2018, 2019. And I think we as a community, as computer scientists, as people who are interested in interpretability, have a real opportunity here to make sure that that regulation, like the definition of that, is going to be decided in courts. But we need to be able to come up with proposals of what we think interpretability should mean and what the reasonable definition should be. Otherwise, it's going to be decided for us. Right? So there's kind of a pressing need here from a legal perspective to come up with operational definitions of interpretability. So in all of these cases that I described, I would say the common thread is that there's a fundamental incompleteness in the problem specification. And I want to distinguish that from the concept of uncertainty. For example, if you are trying to track a missile on a radar, the radar does not exactly pick up where the missile is. There's going to be some uncertainty, and you have this ellipse about where you think the missile is. You get your next set of measurements, and it decreases your uncertainty, or maybe it increases it because it's something unexpected. And now maybe you can turn on different kinds of radar, and you can use that to determine, further hone your estimates. But this is a closed system, right? You have a set of measurements, and you can very well quantify the uncertainty, right? So in that sense, the problem specification is uncertain, but it's not incomplete. And at the end of the day, you're going to have to make a decision with that uncertainty, and we have rigorous ways of decision-making under uncertainty. That's an entire branch of CS. So that, if you're living in that scenario, you don't really need interpretability. There's no human in the loop necessary required, because at the end of the day, you're just going to have to make the best decision you can given the uncertainty that you have. In the examples that I've described here, in contrast, you have this fundamental incompleteness. There's no way around the fact that if you are trying to create scientific hypotheses, you don't know exactly what you're looking for, and you need some sort of explanation to help you generate those hypotheses. Or if you cannot write down all of your safety scenarios in terms of unit tests, then you need the explanation. There's a fundamental thing that you cannot unit test your way out of this particular situation. Right? So that's one thing to keep in mind, because I guess there's various debate about whether interpretability is needed or when it is needed. And this is the definition that I like to stick with, or reasoning that I like to stick with in terms of fundamental incompleteness. So before I go into talking a little bit more about ways to measure interpretability, I'm just going to give you a little teaser, a taste of the sorts of things that we're doing in our group, just one little short vignette, a little story. So this is work that was just accepted to ICHCAI, which we are calling Right for the Right Reasons. And here's the main idea. So we have, let's say we're interested in creating some sort of we have a differentiable classifier, such as a neural network. And so we have some set of outputs, and we have some inputs. And again, the choice of this function can be anything, like a neural network. And then we have some set of weights that it's parameterized by. And then if we have that, the question could be, are there multiple qualitatively different classifiers? And why might we be interested in that? Well, maybe there's these reasons over here where one of them might be unsafe, or it might not be reliable. It may be the case that one has some subtle issue with it due to a confounder. And so without the information of why it's making the decision, we can't tell for those sort of things. But if the classifier can tell you why it's making the decision, and we can find multiple classifiers who make the same decision for different reasons, then maybe we can try to give those to someone and have them decide which is the best one, which is the one that they like. And maybe just exposing the fact that there's multiple different ways to get the same level of prediction accuracy with different types of classifiers is also kind of enlightening to them about the nature of the data set that you have on hand. The way we do this is we're going to define our explanations in terms of the gradient. So if you try to change your value of the input by a little bit, remember that x is the input. If you change the value of the input by some amount, how much does the output change? So if you have an input that is very sensitive to, then that is something that should be upweighted in your explanation or be part of your explanation. Whereas if it's something where changing this x doesn't really change your output, then maybe it's not an important feature. So input gradients have been used as a form of explanation. This is not new to us. Have been proposed as a form of explanation in the past. And the nice thing about these is that they rely on derivatives. And derivatives are very easy for us to compute. They're very fast compared to perturbation-based approaches. So there's a lot of other approaches, such as LIME, that take the x, perturb the x, and see what perturbations of x result in the biggest changes in y. So that's another way of doing your sensitivity analysis through perturbations. We're doing that now on an infinitesimal scale with derivatives, the advantage being that they're super fast. And now what we can do is we can say, if you're given one set of weights, let's find a different set of weights that are not allowed to use the gradients that were large in the next round. So round one, you create your own classifier. Round two, either someone provides some annotations and says, actually, these were bad, like don't use this information when making this decision, or you just try to find a completely different solution. Right. So I'm just going to give you, again, this is a short story, so I'm just going to give you some examples of how this sort of system might work. So here we have an example where we're trying to classify these 5x5 images into two categories. And the choice of the category can be made in two different ways. So it can be made depending on whether the corners of the square match in color or not. And it can also be made based on whether these top three elements of the square match or not. And so there's two different ways of doing the classification that are going to lead you to exactly the same classification accuracy. So in the first round of the classifier, so this is accuracy. In the first round of the classifier, we're doing, again, this is a simple classification problem, so you get 100% performance, and it's mostly picking out these corners. Second round, we say you're not allowed to use the information that was highly weighted in the first round. Find me a completely different classifier, or as best as you can. You have a parameter that you can tune. And so the second round, well, there is actually another example that exists, another choice that exists. So it gives you that choice out here. And then you go to the third round and you say, actually, now I want one more. Can you do it for me? And it tries. And it's mostly picking up noise. And the accuracy goes down. So this is a very simple approach, a very fast approach, because again, it's just based on gradients, computing gradients twice, essentially. You need to be able to take your function, differentiate it, and then you need to differentiate it again to be able to compute sensitivity to the input gradients. But that's all you need to do. And then we can do this on more complicated settings. So here we played a similar game with 2 UCI data sets, iris and breast cancer. And what we did is we took the outputs and we glued together examples from these 2 different data sets based on the outputs. So if it's like flower of type A and tumor of type B, those all get linked together, concatenated together. So now, again, there's 2 rules for making the decision. And here, what we find is that this is a much more complicated data set. There's many ways in which you can, so here, iterations, there's actually many ways you can get very good prediction accuracy. And this is a kind of useful thing to keep in mind, that for many real-world data sets this happens. But you see that the test accuracy, there you go, is lower sometimes because it's picking up, so this was in the training. And then in the test set, we took away basically the flower information, like we permuted the labels. So the right thing to focus on was the cancer tissue question. So initially you see that it had picked up on the wrong stuff, and as you go through additional iterations, it ends up picking up on the right things. And there's no guarantee that this is going to happen in that particular order, but the ability to be able to produce quickly, qualitatively different solutions helps you sift through them and try to find ones that are reasonable. And this is the last example I'll give you along these lines. So here we have an example from 20 Muse groups. And these are examples of words that it's picking out in different iterations. So this is being able to distinguish the atheism and Christianity threads, which was used in previous papers on interpretability, hence we chose it. And what you see, again, is that there's many classifiers that have reasonable performance. And you see that the test performance varies quite a bit depending on the different choices of classifiers, because sometimes they end up picking up weird confounds in the data. This data set has a lot of strange confounds that you can pick up on, because sometimes the person posting their name actually ends up being like a really key signal in all sorts of things. And the point here is that this is a much more real setting. You might not know what the right one is, but at least you can skim through the factors that are being used and look at the prediction performances, and you can decide. You can say, I really just don't like that classifier. I want a different one. And you can keep asking it to produce different ones. So this is just an example of the sort of things that we do in our group, where we're interested in creating these sorts of systems that assist in projects that are ultimately going to require a human, because there is a fundamental incompleteness in the problem specification. We know that the data that we have is not enough. The data combined with the problem specification that we have is not enough that a system can just solve this problem on its own, right? There's going to have to be some sort of interaction. And because there's going to be some sort of interaction, we need to be able to provide what is the useful things for us to do. It's useful for us to provide explanation. It's useful for us to provide multiple explanations. Cool. So let's now go back to the evaluation question. Yep.
So one question about this work. Have you looked at making ensembles of these different weight networks?
So the question was, have we looked at creating ensembles of these networks? One could certainly do so. I guess we've been in the mindset that some of these are going to be right for the wrong reasons, and we just wouldn't want to use them at all because they're going to pick up on a confound. But certainly you could use this to create just more robust decision makers, like a way to propose an ensemble that you could then boost or do whatever you wanted with. Any other questions? No? Yeah.
With the news group data set, were any one of those something a human looked at and said, aha, that's more interpretable and that makes more sense than the other ones?
So we didn't do a user study, but just among ourselves, there were definitely ones that made a lot of sense. I mean, so the first one is essentially picking out words like Christian and atheism. Seems very reasonable for the classification task at hand. some of the later ones end up with names of people, and we could look at those and say these are clearly not making sense because they were picking up users and such like this.
So I can imagine it's like PCA or something where the axes might not necessarily have meaning. And you kind of have the same thing there. Like there might be one interpretable model, but you're picking up ones. They're all different combinations.
So the comment was some of the axes end up being interpretable and some of them maybe less interpretable. And so that's a fair point. And one thing that we're working on now is, can we at least limit the number of things that are sensitive to, so you can at least look at them? And so not only give us multiple qualitatively different classifiers, but can you produce a classifier that for any test point is going to give you a succinct explanation? And that's something that we're actively working on right now and is relatively easy to build into the loss function, because now you want to say that the input gradient should not be large, but for more than a certain number of elements for every input. And for different inputs, you may allow different things to be important. But for any particular input, we only want a few things to be important. And this is something that you can, again, easily put into this framework.
I'm just trying to understand, when you say you do a first pass, you find some classifier that seems to work, and you say, oh, I don't like that classifier, it's right for the wrong reason. I'm just curious, does that mean it's not really right, like it's not predictive, or it's predictive, but for some policy reason I don't want to use it?
It's predictive, but for some policy reason, I don't want to use it. And the one example could be that let's say that it's picking up a confound in the data set. So there's this really popular example in the interpretability world of this wolf versus husky. The wolves are usually out in nature scenes. The huskies are usually like in indoor scenes. And so you could build a classifier that says if there's a tree in the picture, it's probably a wolf. And that's a classifier that on your data set will do really well, because your data set happened to have this bias in it that you were not aware of. And so that's an example of where you might want to throw that away, and you might want to say that that's actually not the explanation that I want a different one.
So in some sense, are you repairing the specification that you gave the ML system? You said optimize this, it did it correctly, and now you're just saying, oh no, I didn't want to use that, I didn't properly specify it, I meant find wolves independent of whether or not there are trees.
Exactly. So you hit it right on the head, that I think the case where you need interpretability is where there's something wrong with the specification.
And that's the question I'm trying to get to.
Yeah.
I'm just trying to understand. So I understand that task,
Yeah.
which is for policy reasons I don't want to use that,
Yes.
that classifier. But now I'm trying to connect back to the title of the talk around interpretability, which is the classifier was doing its job. And if I just had to explain what it was doing, I could say, oh yes, and here's why I'd find that. It used the tree,
Yes.
right? Or it used this blood test to decide this treatment, or it used this factor to decide the creditworthiness of this European Union resident or something. It was doing it was solving the problem. I'm trying to decide which is it that we want to select a different set of ML programmers for policy reasons, and which is it we want to know what they're doing. So is it we want to understand them, or is it we only want to use certain types of
Right. So the focus of this talk is going to be around the definition and the evaluation of interpretability. And this is a short vignette to explain, just to make concrete. Like I gave a bunch of reasons why you might want interpretability. So this is an example of a task where you wanted interpretability to be able to check whether the classifier was making its decisions for the right reasons and be able to reject it if it was making it for the wrong reasons. So this is just an example of a situation where you might want interpretability, but there's many. And so we're going to zoom back out into the general question. And this was just one specific example of a situation where you might want this. All right, so the big question is, like in this case, maybe you had someone in the loop, right? Maybe you had someone providing that feedback about, I like this explanation, I don't like this explanation, and you had a system, right? You were trying to build for a certain policy-related task, right? And so presumably, if you were trying to do that, then you have a measure of how well it works, because you have a task in mind, you have an expert in mind. That expert can check, and you can request additional solutions. But now let's think about it more broadly, right? How can you measure interpretability? Not necessarily in the absence, but in the abstract, right? In the more general sense. So one option is to say, well, interpretability, it's like porn. You know it when you see it. And so, or this is a kind of related way of saying it is that we have interpretability by fiat, right? We're just going to call this thing interpretable because we've just decided that this thing is interpretable. And so if we look at various, and these are like really good papers, by the way, so I'm not making fun of any of them, but what I want to point out is that you often see statements in machine learning papers, and I'm guilty of this as well, of the form, you know, certain type of model is the gold standard for intelligibility. You know, our rationales are simply subsets of words. You know, this is just saying, like, clearly this thing is interpretable, right? These sentences are just telling you that, of course, this is the right way to solve this problem. And the thing that when we read this and it seems reasonable to us, there is a face validity to this. Because the whole point about interpretability is that it makes sense to human beings. We're all human beings, so if this explanation kind of makes sense to us, that is cool, right? But at the same time, it doesn't really let us go forward, right? Because it gives us a set of classes that are interpretable, but then what do we do with that, right? We can just optimize within that class, right? Right, so this is what I just said. So if we agree that you know, this, you know, a GAM is an interpretable model, then now the problem is done. The interpretability problem, in some sense, is done. All we have to do is optimize GAMs. But we want to make sure that there's some evidence for these different forms of models actually being interpretable. Another way of doing this is saying that interpretability has to be evaluated in the context of in terms of a real application. So this goes back to my story earlier that maybe you had this application in mind where you were trying to separate those newsgroup posts or understand different tumor types, or in my case, predict meds for different patients. And if you're trying to do this task, you have a clear goal that you want to avoid confounds, and interpretability has succeeded if it allows you to do the higher level task, right? There was some task in service of which you needed the interpretability, and the HCI, the visualization, the human factors communities have definitely embraced this sort of view. You know, the airplane controls are good if it allows the pilot to fly the plane safely, right? That's your ultimate criterion. So this sort of criterion is useful because it's a real evaluation on a real problem. Like, no one's trying to like make up something and say, clearly this form of model is interpretable. You have hard evidence as to whether or not the model is actually interpretable. But it may be costly to perform those evaluations because you have to do it in the context of a real application. And you might be curious about whether or not it generalizes. For example, the human factors community in aerospace has spent a ton of effort trying to understand how flight controls should be set up. Right? There's a lot of really great science behind that. But now, if I'm trying to build some sort of other user interface, what can I learn about the airline flight controls, say for a self-drive or semi-autonomous car? Right? It's not necessarily clear exactly how the transfer happens, right? And that's the part that maybe we want to make a little bit more explicit. So the question that we want to get to is that are there more general proxies? And so things like sparsity are often brought up. People often cite this 7 plus or minus 2 rule that says, like, how much can people hold in cognitive memory? There may also be ideas of monotonicity, that, oh, I can like something that if I turn the dial, like my accelerator, if I push on the accelerator, I know I always go faster, and that kind of makes sense to me. And if I'm going up a hill or there's a bump in the road, maybe the rate of acceleration might be slightly different, but at least I kind of understand, okay, push on the accelerator, and then my car will move forward or increase in speed. So are there fundamental notions here? And again, the nice thing about having these sort of fundamental notions is that as computer scientists, we can optimize these things, right? We love this because now it's like a mathematical function that we can work with. But again, the issue is we need to make sure that it's evidence-based, that we need to be able to understand where is this assumption coming from, or is it just something that's reasonable, that looks reasonable to us, or is it something deeper? And this is important not only just from a philosophical, I care about science perspective, but I think it's also important for being able to make comparisons, right? Like if something is just a little bit sparser, is it actually more useful for some downstream task? So what I'm going to propose here is a spectrum for evaluation. So I'm going to split it into two pieces in terms of quantitative and qualitative forms of evaluation. And I think the qualitative part is absolutely important. We eventually all probably want to live in this space over here, because then, again, we can optimize it on a computer. But before we get to that stage, we need to think about the other elements. So there's a level of the real application, right? So that's the level that I talked about that, again, you might be thinking of from a human factor standpoint or from a HCI standpoint. And you can measure, did we actually improve some patient outcomes? Or we can just ask scientists, did you like this, right? Was this helpful? Again, we're measuring something in the context of a real application. And then we can think of it one level more abstractly. We could say, can people describe what factors should be changed in order to change the outcome? Right? That seems like a reasonable sort of question. If the explanation I've provided you is a good one, then you should be able to forward simulate what might happen with counterfactuals. And then you may also ask more qualitative things about the model itself. And then finally, you have the level of what I'm calling proxies, or things that we can think of in more very abstract terms, like functions. Are the features sparse? Does it look reasonable? And my claim is that we need to move in this direction of real stuff should be informing the functions that we are using for optimization. And keeping in mind that as we go up the chain, things are going to get more specific. So I think that the top layer and the bottom layer are pretty clear to probably are pretty familiar, comfortable to most people. You can think about optimizing for like L1 like sparsity. That's like really conceptually simple for us. We can also think of measuring, whether patient outcomes improved or not. And the part that I think is really understudied, and I think that we should all be thinking about and investing in, is really understanding the glue between those, which is the cognitive science layer. So I'm going to talk about how we might think about this layer and some specific hypotheses that I think are useful for us to think about as a community in this space. So in terms of a general form for human evaluation of explanation, so here we have this very specific question, right? Did we improve patient outcomes? Like, what's the equivalent of that for just a quality of explanation? And in this case, we're not interested in whether the explanation is correct, right? So keep in mind that my explanation for like any prediction could be, because the sky is blue, right? And the thing is, that explanation is not predictive at all, but it maybe is easy, but it's still easy for you to understand, right? Like you understand what I'm saying when I say because the sky, I predicted this tumor type because the sky is blue, right? Like you can understand it. It's very understandable. And the reason why we're going to focus on understanding is that the accuracy part of an explanation is actually very easy to quantify. That if I have a classifier that predicts malignant tumor every time the sky is blue, I can check that and see how good a classifier that is, right? That's a quantitative thing that I can check. And therefore, it's not a complicated problem in terms of evaluation. It's very easy to do. The hard part is measuring whether the explanation is good in terms of does it convey some sort of understanding, right? Does the human understand what the person is talking about? So in terms of a general form for a human evaluation of explanation, what we're proposing is being able to evaluate some sort of counterfactual. So if you ask the person, how do I need to change the inputs, right? What if I change the inputs to change some prediction? So maybe I have a specific data point. I want to change the output, right? What inputs do I need to change to get the output to change? That might be a very general sort of question that I could ask. I could also ask about the internals of the system. I could say, actually, the input stays the same. Is there an element of the explanation that I would need to change in order to get the system to predict some different output? And finally, I could say, we could also think about this mismatched objective thing, saying that actually, what would I need to change in the criteria to be able to get a different output of interest? So there's all sorts of permutations of this, but this gets to this fundamental idea that's very common. I mean, when you're in school, how do they test you on whether explanations work? It's like whether you can predict things, right? You do a science experiment and they ask you, now what's going to happen when you mix chemical A with chemical B? Can you tell me the formula that came out, right? So we're essentially asking humans to be able to answer similar questions, but now instead of grading the humans, we're grading the system. Because if the human can answer the question, then it means the system did a good job of explaining whatever it's trying to do. So now we can move on to some specific hypotheses. And again, I'm really curious to get people's feedback and input, and I think it's really important for us as a community to be thinking about this layer of cognitive science, which is not really well thought through. And so one hypothesis is that in terms of being able to generalize, tasks have certain covariates. So we can think about where is the fundamental incompleteness in the problem. Is it in the structure of the data, right? Are there just weird confounds that may also be in the inputs as well? Is it in the reward functions? Is it in the internal features? And maybe different, all of those cases might have different needs, right? And it's important for us to think about the fact that interpretability might not be there might not be one thing that is interpretable in all scenarios. And the form of the explanation you need may be different for different settings. Another important distinction is the scope. Like, are we trying to understand the full model? In many science cases, we are, right? You have a big batch of data, and I want to understand, what does this tell me, this big batch of data, tell me about disease progression and different subtypes and autism, right? I'm not interested in any particular patient. I want to understand the overall trends. So at that level, I'm trying to understand explanations for the whole system. On the other hand, if I need to make a decision for a specific patient and say, do I treat this patient with this drug, then the form of explanation I need may be very different. And in particular, the need of how quickly the explanation must be utilized could be quite different in these different scenarios. I might be willing to spend a couple of hours looking at the output of some global science discovery sort of system, whereas like if there's something that needs to be made, a decision that needs to be made at the bedside, maybe you only have on the order of minutes or less to properly understand it. So this seems all very reasonable. And what again, I said this talk is going to be a lot of philosophy. I'm encouraging people to maybe think about that as you're building your systems and designing your systems, and thinking about what are the natural ways in which you can bin these systems, and think about the different needs that are associated with them. The other hypothesis that I'd like to float out there and have people consider, this is a little more abstract, is that explanation actually has two components of it that we maybe can think about distinctly and separately. So the first component, it's pretty light, is structure. So if we think about agents, actions, and outcomes, maybe we have some explanation that says that here A goes to B goes to C, right? That's the form of my explanation. My explanation, and to ground that into a specific example, maybe you give a vasopressor, it constricts blood vessels, it increases blood pressure. So if I'm trying to increase blood pressure and the system says, give vasopressors, this might be the explanation that comes out, right? And that explanation has a certain structure, which is A to B to C. And it might have all sorts of different forms, and different structures here may be more or less understandable, right? Here's where we might run into issues of like, if too many factors are involved in this explanation, we just can't follow it, right? We can't do those counterfactual reasoning. Like if there was some other factor going in here, maybe we wouldn't be able to do the reasoning about what would happen if something else changed and something else changed, et cetera. Maybe it's going to get too hard. And maybe that's a fundamental quantity about humans, right? That there's certain types of these structures that we can easily handle, and there's other structures that we can't handle. So if we're in that regime, we can think abstractly in terms of like A to B to C. Right? There's another key component, and that other key component is thinking about the cognitive chunks. So that what happens when we ground each of these variables in like a specific concept. And here, it's important to remember, so there, again, this off-cited 7 plus or minus 2 rule, it's not 7 plus or minus 2, actually, 7 plus or minus 2 what, right, is the question. So if I give you the acronym CIA, is that one thing to you, or is that 3 letters that you have to remember? It's probably one thing, because you have a concept for that. It's a single item. And so one thing that's really important in these very large data sets is first identifying what are the cognitive chunks. So clinicians might have a word for a collection of diseases. We work with billing codes a lot, and billing codes are like insanely specific. and so you may have 25 or 30 codes that correspond to epilepsy. And so but the clinician has a word for epilepsy. So an explanation does not need to, we don't need a separate A and a B and a C out to some large fraction for all of the different forms of epilepsy. We could collapse it into one thing, right? Similarly, we may have situations where certain relationships might be really well known. For example, a vasopressor constricting blood vessels. That might be known science. Right. So the question was, if you end up providing a more succinct explanation, but there were multiple that only pulls out the biggest factors, what about all the multiple other tiny factors that may also be affecting the explanation, and do you have an ethical reason to expose them? I think that's very problem dependent. For example, if you just want to be able to overall be able to say, like, if changing none of those factors is going to change the outcome, the final prediction, maybe it's safe to ignore them. If those other factors can co-vary as a chunk, then maybe it's important to expose that to say that actually if this larger cognitive item changed or this larger correlated item changed, then actually the output could be different. I think that comes back to this accuracy trade-off that I mostly said I'm not going to worry about, but it's this question of any form of explanation is not going to be perfectly faithful to your model, assuming that your model is some really large, complicated system. And so that's going to have to be another user-defined threshold of like how much accuracy am I willing to sacrifice. And if you are not willing to sacrifice a lot of accuracy and your explanations, you still need your explanations. Maybe they're going to suffer in quality in the sense that maybe you are going to have to include more things. So all of this stuff I see in the setting where you have a threshold on accuracy. And you say the explanation actually has to be at least this good. And given that the explanation is this good, how can we limit, how can we make it more of higher quality? So it may be the case that certain structures are easier for people to understand. And it may be the case that like A can be grounded in something that actually consists of a lot of items. And maybe even this link from A to B, if we are finding that it takes people a lot of time to traverse things of a certain length, but maybe it takes people less time to traverse things of a shorter length, right? Of things that they know, that maybe that effectively reduces the length. Right? So here, these are hypotheses to keep in mind. And as you're building your systems, one thing you can think about is, like, since interpretability is such a human concept, right? We can't really think about it without thinking about what is the language of the human. Like that's maybe another key idea to keep in mind, is that we need to have like basically a dictionary of what is the language of the human to be thinking about this. All right. So I'm going to mostly wrap it there. That investigating these hypotheses and these sort of questions I think are really important because they're going to lead us to understand, are there model classes that seem to work well for certain settings? So that was the first hypothesis, was a task-hazard and covariates, right? So those are our settings. And then are there model classes or regularizers, and maybe that has to do with the forms of these structures that we consider okay or not okay, that are best for certain settings. And these are a set of experiments that we could do, that we should do, that we should be supporting each other as a community to do. Because I think that until we really get a solid sense of like the cognitive science of explanation as it relates to really specific machine learning tasks, we're not going to be able to make comparisons between different methods very rigorously. And we also may end up just optimizing the wrong things, right? You may end up optimizing for some form of some function and find that it's not actually the function that you needed to do the task at hand. So in terms of the big takeaways that I want us to be thinking about, and again, leaving plenty of time for discussion, the first is that when do we need explanations? So we need explanations when there's a fundamental incompleteness in the problem specification. And it's important to be honest about that, because there's many cases where that just doesn't happen, right? Like if the system is operating independently, does not need any humans, the problem is well specified as well as it can be, then it's great to just throw like a super predictive deep model at it and that's the best you can do, right? And that's what you should do. So thinking about when do you actually need explanation. And also this point that there's a spectrum of valid evaluation going from just like, what's my L1 sparsity score to how well does it perform in a particular embedded task setting. And to do this properly, we're going to need more connections to cognitive science. And my claim is that a relatively modest effort in terms of doing some of these experiments could have huge payoffs, because maybe we're optimizing too much for the wrong things. Where if you have papers that say, I can get something that's 5 sparse and somebody else can get something that's 4 sparse, does it actually help, right? Like, was that worth it? Was that extra effort worth it? And maybe there's something completely different that we should be focusing on that we're missing out on because we haven't thought about it. So the main thing that I want to encourage us all to do is let's be rigorous about this question of interpretability. That there's a ton of research going on in this area. There's not really consensus on how to evaluate it and how to think about it. But as we go forward, we're going to need to be able to make decisions about which system is better for a particular task and when have we reached satisficing. Because interpretability, I think, is definitely the sort of thing where you reach a level where people can understand it. And once people can understand it, then in some senses your task is done because you've managed to communicate. So cool. So I'll leave it at that. I'd love to hear questions, opinions, and discussion.
Thank you very much. That was a wonderful talk. I think the connections with cognitive science are just very fascinating and raise lots of questions. One that came to my mind was, we know that people are very sensitive to framing effects. The same information presented in 2 different ways can be very different in how understandable they are. How do we control for that when we're evaluating different model classes? And does there need to be a little subfield of this of like, let's try to find the best framing for these neural networks or models?
I think that's another really important question. And so I didn't really get into the, how do you set up the system that provides the explanation, and also the more general UI issue of how you present this. I envision early experiments can probably be done in sufficiently abstract settings that you can try to control for as much of these effects as possible. But certainly in a real situation, that's going to be another axis that needs to be carefully discovered.
So it seems that there is an inverse relationship between the performance of a model and the interpretability of that model. So for example, logistic regression is extremely simple, doesn't often perform that well. It does well, but most importantly, it's extremely interpretable because each of the coefficients in the model, you can say, okay, this is a big positive effect, or this is a big negative effect. Whereas more complicated models, deep models, they tend to be very hard to interpret. Do you think that inverse relationship is inevitable? Is there a law saying that the better a model performs, the more unintelligible it becomes, or is there some way around that?
I don't agree with that. So Cynthia Rudin quotes this paper, which I'm forgetting, that says that many times there's many models that perform reasonably well. That oftentimes you can find multiple models, and certainly our anecdotal evidence with training deep models is that you can get multiple deep models that produce similar predictive scores, and the question is, can you make some of those more interpretable than others by, say, involving fewer dimensions? So I would and I also push back on the fact that is something like logistic regression interpretable? Because if you've got 100,000 dimensions in your logistic regression, and they are covariating in all sorts of funny ways, the top weighted things might mean nothing, right? And so I actually don't agree with the fact that simpler models like a linear model or generalized linear model are actually more interpretable than deep models once you're in high dimensions. And one direction that I'm really excited about in terms of avenues is this notion of local interpretability. That is, for any particular explanation or input, can you provide me an explanation that is succinct? And I think there is hope, even with deep models, because you can, also with deep models, you can pick out intermediate layers, right? You can think about the cognitive chunk. So if you can identify a layer in the network that largely activates when there's a cat in the picture, then you can say that the reason why I've done this classification for this being like the Wizard of Oz as a scene from Wizard of Oz is because I see the lion here, and like I picked out the lion in the picture, right? So I think the two things that we have going for us is that we may only need to explain one instance at a time, and that we have access to we are kind of assuming that we have access to a library of cognitive concepts. And I think so there's absolutely hope for being able to explain deep models or find deep models such that these properties are also true and you don't have to sacrifice on prediction. You might also argue that if the model is getting you tons more predictive accuracy in a certain situation, like I can't think of situations where that would happen where you're not maybe picking up like a weird confound, right? Like maybe you're getting a load more accuracy, but it's because you picked out some weird correlation that maybe is not true. Yeah.
So it would seem like there's a difference between experts and non-experts in terms of how explainable something is, where like the person who's flying the plane every day knows exactly where to look and what they're looking for, and they want to make the decision really quickly. Do you think that if the distinction expert, non-expert is enough, or do we need like gradations or experts in different fields in terms of understanding how these proxies would generalize, to other fields or other situations?
I think that's a great question. And one thing, so this is a hypothesis, an empirical thing that needs to be tested. And I should say, so this is all in discussion with Bean, Jesse Johnson here, Sam Gershman at Harvard, where we've been talking about like experiments and hypotheses. We believe, or a hypothesis that we think is testable, is that there are still fundamental aspects of like control processes that humans can understand in terms of this chains of causation or agents and actors. And that part, and the hypothesis is the difference between experts and non-experts is not necessarily that the expert can hold more in memory or hold different structures in memory, although certainly people get trained to do that. So that's the thing that we should be absolutely aware of. But we're curious how far you can go with this hypothesis that maybe experts just have different chunks. So we figure out like general structures that are generally explainable, and then we can sub in chunks that experts have, because the doctor might have a name for something or a way of understanding a particular device that somebody else doesn't have access to. And can we plug that in? And it's an open question.
Squeeze in one last question. I wonder if there are fundamental differences in the area of interpretability between domains that are deeply studied, like healthcare, and domains that are brand new, like how to maximize clicks on ads. That the existence of a deep spectrum of human expertise, on the one hand, it puts very different pressures on our machine learning systems in that context.
So just to make sure I understand, so you're saying that there are some cases where there's a lot of domain expertise, and there's cases where there's less domain expertise in terms of what the explanation would provide?
Yeah, absolutely. You might observe that a lot of the most interesting applications of machine learning recently have been in areas that are not that deeply studied, whereas we've struggled to have equal impact in healthcare. Maybe because of the amount of learning that's already happened.
So I think so there's potentially the claim that maybe there's a lot of learning that has already happened in healthcare, so maybe there's less to advance on. I think it actually does come down to this incompleteness in problem specification that makes a lot of these real-world tasks harder than tasks that we have created, like somehow human created. So like the click question is something that's very closed in the form of we have a system, we can measure whether something changes click rates or not. And so there's a way in which the problems, so to the extent that you define the problem as we want to increase certain rates, right? It's very measurable and it can be done in a closed loop fashion, and I'm not sure if it requires interpretability. If you're asking the question more broadly, if like uptake of machine learning or like value provided by machine learning in certain settings. And I think it is entirely fair to say that the value that machine learning is added in settings where the problem is not fully specified and where there is this incompleteness, where you're measuring things in the EHR and the EHR are super messy, has not necessarily been there because we haven't really figured out how to communicate and measure in those systems. Awesome. Thank you.